Hi, I'm Paul Battaglia, and this is section 8.5. Now, students have a knowledge of some series, geometric, p-series, and certainly they've been seeing some tests. Now it's time to look at series that have alternating terms. So the essential question we would like students to be able to answer at the end of section 8.5 is, how do you determine the convergence of an alternating series? Now, a great way to start off is by looking at theorem 8.14 in more detail. See, students need to be cognizant of the conditions that have to be met in order for the alternating series test to apply. So we spend some time looking at the idea that the limit of the sequence, or the series in this case, must approach 0 as n approaches infinity. And then that second condition, well, that's a little tough for students. So the way I like to phrase that is, I tell students we need to look to see if the terms of the series are decreasing in magnitude. What that means is, if we ignore the sign values, positive, negative, and we just look at the terms themselves, are they getting smaller as we expand the series? And if both of those things are true, then the series converges by that alternating series test and by theorem 8.14. So these are things that students need to be aware of. Now, when faced with the series in general form, it may be hard to see some of these things. The limit is usually easy to find right away, but the second condition maybe not so much. So I like to tell students, list out a few terms. Take care in doing n equals 1, 2, 3, 4, and see if those terms are indeed decreasing. Now, let's look at example 2. Example 2 does a great job of kind of showing students we don't want to become creatures of habit. So what I mean by that is, it's so common to see -1 to the n power, and students often see that, and that kind of indicates to them that we might be seeing an alternating series here. But example 2 shows them that we could have -2 to the n power, or really any number for that matter. But we need to be cognizant of the fact that it's not always -1 to the n. Now, what I like about example 3 is that it helps us connect mathematical practice number 3D, apply an appropriate mathematical definition, theorem, or test. See, in that case, we've actually presented 2 different examples so that we can show students what it's like when either of the conditions necessary isn't met. So one of the problems will actually show students a series where the terms are tending to 0 as we take the limit as n approaches infinity. However, the terms themselves are not getting smaller. And then we flip it up and we say, okay, let's show you a series where the terms are getting smaller. However, the limit is not tending to 0. So a very good example to look at here. Now, there are some common mistakes we want to discuss with students, and the first one is really all about those conditions. Students need to make sure that they're looking to see that both conditions are present, not just one. Now, alternatively, they hear that we're looking at alternating series, and they may see a series like positive, positive, negative, negative, and say to themselves, well, looks like it alternates to me, but it really doesn't. What we're looking for is that the terms alternate consecutively. Positive, negative, or vice versa, negative, positive, negative, positive. When we see that, we know now that the alternating series test might come into play. The other thing we see in example 8 is a rearrangement of series. And what's interesting here is that if I throw up this series, it really gives students problems in trying to form a conclusion or a hypothesis. I'll just simply put 1 minus 1 plus 1 minus 1 plus 1 dot, 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 forever. And I ask them, what do we do with this series? And I say to them, well, tell me what your conclusion is. And some of them will tell me that it's 0. Some of them will tell me it's 1. Some of them will tell me it's -1. And then I start to do something almost evil. I start to place parentheses around the terms and say, well, what about if we group the first pair, then the next pair, how about the third pair? And what I'm really looking for is I'm looking for that student to say, well, wait a minute, why do that? What's preventing you from saying, well, let's group the first 3, and then the next 3, and then maybe the next 2? That's what I need to hear from them, because now they're thinking about, while this is maybe a little bit beyond the scope of what they might see in terms of maybe an assessment of mine or an AP exam, they need to be thinking about how we can maybe rearrange these series and where it might take us. Now, let's take one last look at example 5, which is really a good example to get students ready for a twist on the entire concept. See, we're looking at the alternating series remainder. And the question we're asking is, how many terms are necessary to approximate the sum from the series accurate to within 1/1000th? This is a fantastic question because it makes students start to think about, all right, we are dealing with an infinite series, but these series are used to approximate things. And when we're looking at accuracy, it does matter how far we take out the terms and how many terms we use. Obviously, the more terms we use, you would think, the more accurate we get. And then lastly, I think students need to be aware of the idea of absolute convergence. This is something that I found my own students overlook on free response questions or any of my assessments. We need to make sure that they understand if a series converges absolutely. So in other words, if the series of the absolute value of a sub n converges, then a sub n itself must converge. So a little tidbit there. Spend some time on absolute convergence for sure. I hope you found these tips helpful, and I'm sure you'll find much success in section 8.5.